In this example, I'd like to tie together a lot of the previous formulas that we've given and go through the exercise of finding all of the quantities of interest in a basic transmission line. I'll just preface this by saying that I know there's going to be a lot of calculator punching, specifically if you have a fancy calculator that can do complex math pretty straightforwardly, then there's definitely an advantage to this. From a test writing standpoint, one of the challenging things is that with the amount of complex algebra going on, it's really hard to come up with clean math problems where the numbers just work out nicely. But I think that there's still the benefit of going through these calculations, making sure you're able to perform them and get the numbers that match up. Let's take a look at this basic setup here. We have VG, which for now we're not too concerned about the frequency. We'll just give the amplitude and the initial phase. It's going to be amplitude of 10 with phase of 0 degrees in the phasor. The reason we're not too worried about the frequency is that we have the basic quantities over here, and the length is defined in terms of lambda. And so since we have the length in terms of lambda, we're not too worried about the frequency, especially if we have the impedances and all the other necessary numbers at that particular frequency of interest. And let's set the input impedance to be equal to 25 ohms. Let's just start by working our way through all the steps. So the ultimate goal is to find all the quantities that I had listed in the previous discussion that we would be interested in. So the voltage going in, the current going in, the voltage at the load, and we'll just go straight to the time average power at the load. I'll number this according to the steps in the lecture notes and the lecture discussion. So first of all, let's try to find beta L and use that to find the input impedance. So beta is 2 pi over lambda. If lambda is given in units of wavelength, the lambdas cancel out and we get 3 pi over 4. This is the quantity that goes into the tangents. With that, we can then calculate the input impedance, which is 50 over the load, 50 plus J50, plus J, the Z naught, which is 50, and tangent of 3 pi over 4, all over, and then the denominator is swapping these two numbers. So 50 plus J, 50 plus J50, tangent of 3 pi over 4ths. And so this is a situation where, at least in the first step, we're able to get nice numbers. But if you have a fancy calculator or access to just straightforward complex algebra calculators, you'll find that the input impedance is going to be equal to 20 plus J10 ohms. What's the next step? The next thing we want to find is how much current and voltage actually go in to the transmission line. So V in is just going to be the voltage divider between ZG and the input impedance. The input voltage is 10, phase is 0, so e to the J0 is going to be equal to 20 plus J10 all over 20 plus J10 plus ZG, which is 25. And this is where the pretty numbers kind of die out, but if you punch those into your number crunching accoutrement of choice, you'll find that the amplitude is going to be 4.851 J, then 1404 degrees volts. So I think this is not a pretty number, and it's just a bunch of complex algebra, but I encourage you to follow along, punch this into your own calculator, and make sure that you're able to come by this number. It's a nice little check to make sure that you can at least gain some familiarity of these concepts by going through the motion. And similarly, the input current is going to be the input voltage divided by the input impedance, which is going to be 4.851 e to the j 14.04 degrees. divided by, in this case, the input impedance. Let's just write out how to convert this into polar form. So 20 squared plus 10 squared square root e to the j, and you'll take the arctan of the imaginary over complex. And if you work through that, you'll find that it is 0.2169 e to the j 12.53 degrees amps. So you see you have the voltage and the current, and in this case you see there's a phase offset between the two. So you know that if you were just to calculate the instantaneous power everywhere, you're definitely going to get slightly less than the maximum possible value. And that stems from the fact that your input impedance is a complex number. So step 3, we're going to find our reflection coefficient. Remember, it can also be a complex number. So it's nu, which is our load, minus old, over nu plus old, 50 plus j, 50 plus 50. And if you convert that into polar form, you'll find that it is going to be equal to 0.4472 e to the j 63.43 degrees. Now with this reflection coefficient, you can then calculate the VSWR. Guess I didn't specify that you want to calculate the VSWR, but you might as well. And this is where having this 0.4472 magnitude in polar form pays off, because you can just directly pull that number out. It's 1 plus 0.4472 over 1 minus 0.4472, which is going to give you a VSWR of 2.62. Next up, we want to march our way towards finding the voltage at the load and the current, and so that we can use that to find the power at the load. Remember, to find the voltage, we first need to, at the load, we first need to find V1 plus, and we do that by coming up with an expression for the voltage everywhere. So we start with Vn is going to be V1 plus e to the j beta L plus the reflected version of that. Plugging those quantities in using this expression, Vn is going to be equal to V1 plus e to the j 3 pi over 4 plus, and we have our gamma L here, so 0.4472 e to the j 63.43 degrees. So that's our reflection coefficient times e to the minus j 3 pi over 4. And that whole thing is going to be equal to your Vn, right? So that whole thing is going to be equal to 4.851 e to the j 14.04 degrees. If we combine all this into a single complex number in polar form and then divide that over here, divide that under Vn, so if we take this whole thing and divide it over, then we are able to find that V1 plus is going to be equal to 7.670 e to the minus j 139.40 degrees. Now taking this, we're now in the home stretch. We're able to solve for VL and IL. So VL will be equal to V1 plus times 1 plus gamma. So now you're just crunching numbers at this stage. So if I were to write out what we're actually plugging in, we have V1 plus, which is 7.670 e to the minus j 139.4 degrees. And then 1 plus gamma is 0.4472 e to the j 63 degrees. If we do a bunch of cleaning up, you'll find that VL is going to be equal to 9.701 e to the minus j 120.97 degrees. And then separately, your current is just going to be VL divided by ZL, where ZL is this complex number over here. And if you plug that, churn through it, you should find 1.372 e to the minus j 165.97 degrees amps. So the final thing that you want is, we'll just use this little corner here, is the time average power density, which is going to be equal to 1/2 the real part of this 9.7 e to the j minus 120 degrees times the conjugate. So 1.372 e to the, and then don't forget to change the sign because it's conjugate. Oh, 100 and positive 165.97. So if you multiply those two numbers, take the real part in terms of, so specifically just multiplying the phase, plugging the phase into a cosine and multiplying it by 1/2 of 9.701, you should end up with 0.470 watts. So again, this is a lot of number crunching, but just keep in mind the basic procedure. You start with finding the input impedance. You take the voltage divider so that you know what the input voltage and input current are. Next step, ultimately you want to find what the power is at the load, but before you do that, you need to find gamma L. And for the purposes of all the things that you need to know for this class, also make sure that you know how to go from gamma L to the VSWR. But once you have gamma L, you can use the fact that the input voltage is going to be equal to V1 plus as e to the j beta L plus gamma times V times the forward going wave, and setting that equal to Vn will give you everything that you need to eventually solve for this V1 plus. And once you have the V1 plus, you can find the voltage at the load by multiplying it by 1 plus gamma, and you can find the current at the load by dividing it by ZL. And that will enable you to calculate the time average power by just taking the voltage and multiplying it by the conjugate of the current. Easy peasy, as long as you didn't scrimp on your calculator purchase.